combination of all kind of aspects of policy gradients. There is a lot here to talk about, but at the end of the day, I don't know. It feels there is not so much. So it's like this feels like a totally weird lecture because on one hand, it feels like that I can only tell you like half of the story because of time. At the same time, everything that I tell you is kind of like wishy-washy, and it's not like the usual like you have a nice theorem and then like okay that means something. It is more like, oh yeah, we can do this, we can do that, we can calculate things like this or that way, and yeah. Anyways, hopefully this is going to lead to a good discussion at the end. But there are some aspects of this lecture which I like. I like the beginning, how it starts with the policy gradient theorem. And so let's start with that. What I call the policy gradient theorem, other people may call other things the policy gradient theorem. Okay, so what is this theorem saying? So let's say you have a set of probability kernels over the actions from the states which are parameterized with some parameters that take values in some Euclidean space. So we can just write something like this. So if you have, okay, like this notation is, so the theorem holds for general action spaces and everything. You can make it very general. If I write anything like this, this is already somewhat special because this somehow indicates a probability or a probability mass function, or yeah, but like if I keep it very general, then you'll be lost. So it's kind of in between. So let's say we try something simple. The action space is discrete. Then this would be the probability of taking an action in a state if the parameterization is x, and x takes values in RD. Then the performance of a policy is measured simply by how much total expected discounted reward it collects if it started from an initial distribution over the state space. Okay, so mu is a measure of the state space. You start a policy from there, you will follow it, you're in this MDP, generates trajectories, generates rewards along the trajectories, you sum them up, discount to take expected value, that's it. That's the performance metric. And
there's supposed to be a transpose? It's an inner problem?
Okay, notation. Yeah, so we remove all the clutter.
Okay.
This is called a friend school. We don't do transposes or anything like that. Actually, the proper interpretation is that if you want vectors, like S is discrete, this mu could be a probability vector, but this should be a row vector. Because then we don't have to write transposes. And we don't have to write inner products. And for measures, like if you take a measure and you multiply a function with a measure from the left, it just means integration with respect to it. So that's the friend school. It's beautiful because it's very concise, and at the same time, it takes some time to get used to. Anyways, so it's all fine. Okay, so what does the theorem say? Well, we want to know how to move the parameters, and I guess here everyone knows about, like you just follow the gradient, and then it climbs on a function. So you want to know what is the gradient of this thing. At some parameter of interest. And this seems like, okay, so this is very compressed, right? So this is the value function. we know how the value function can be computed. It's like, oh, take this inverse of this policy evaluation operator, this I minus gamma pi of x, inverse, apply it to the reward function. That's what you get. And then you just have to differentiate, right? And then you're done. You can differentiate inverses, it's all fine. It's still a bit complicated. Or you can write it as an infinite sum, right? Of all the discounted things, and like, no, you can differentiate every term. If you're lucky, then you can move the derivative inside the sum and so forth. So that's kind of like the thing that you're talking about. Like, how do we get something that is easy to evaluate? And so this theorem is going to say that, well, you can actually get something quite nice. All right. And this is the following. So you take the discounted, the discounted occupancy measure induced by this policy when the parameter is set to theta naught, and you start a policy from nu, and you multiply it with the derivative of this thing. So how do I call this? I don't know. This doesn't really have a name, but it's something super simple. So this thing here, so this is just the policy evaluation operator. And one day I'm going to adapt, so the next level for the French school, Dadash's notation. When I just drop this m, I will just write pi of x here, because it's kind of the same idea. So this thing here, what is it? It's like, okay, if you have, okay, I said that we can sum over the actions. We have countably infinitely many actions at most. Then this is just this. You take this state action function, whatever is that, and then you map it to a function that is just over the state, so projecting away the action component by taking average with respect to, like the policy component. And so a short annotation for that for the future would be just this. That's also nice. But like, I was not that brave, and I was writing this lecture notes. So. Anyways, this is the theorem. It has some conditions. Doesn't hold always. So under some technical conditions. And you can read in the lecture notes what the technical conditions are. They are sufficient and necessary in the sense that, like, if you don't have any conditions, then of course it's not going to hold. The proof is based on just like, okay, how partial derivatives lead to total derivatives. So it's totally simple. It's nothing much more than that. And why is this great? So this formula is great because this seems complex because of this complication with the value functions. And here, taking the derivative with respect to something simple like this, like for every state, like you just, okay, if you don't have too many actions, like finitely many, then you can move in the derivative without any thinking behind the sum. If you have more, or you need to integrate there, and so the theorem extends to that case as well when you're integrating over the actions, and then there's a continuous action space. Maybe you have some, there are some other considerations there. We're going to consider one version of the theorem for that case as well. Still works. So it's beautiful because this becomes super simple. If you have the discrete action spaces, you just move in the derivative. So evaluating this derivative is a no-brainer. So here, this at S, okay, let's say we have finitely many actions. Then you just move in the derivative. And then, okay, if you have, I don't know, seen statistics, then one of the tricks that people do is that if you're taking the derivatives of probabilities, so here we would need to take the derivative of this. This is a probability of taking action A, right? Then you can write this as taking the derivative of the logarithm of the probability times the probability itself. Why? It's because if you're taking the derivative of the log, you get a 1 over, and so you're canceling out that. 1 over the probability cancels with the probability, and you can do this as long as the probability is non-zero, so you have to be careful with that. Otherwise, you would need to, okay, that's messy. Let's not do it. And so if you do this, for example, then you can get nice formula like, so now we have this probability still, and now we just have to take the derivative of the log of the probability of taking the action multiplied with the action values. And so this looks like it's an average of the action values correlated with what is called the score function underlying the policy. So this is called the score function method in statistics or other places. Because you want to see it as an average, as an expected value. And why do you want to see it as an expected value? That, okay, it's because maybe we want to estimate these things, and you don't want to run, okay, so there is another sum hidden here, which is over the states. You have these two sums, big sums. That would be very expensive to calculate. Maybe you just want to sample. Nice and elegant, and you can get an unbiased estimate of the gradient very cheaply if you can sample from this measure, and then once you sample for this measure, this is over the states, then you sample from the policy, and then you just like take this value and at the sampled state action pair, and that gives you an unbiased estimate of the gradient. Yes.
So can we sample from that new without rolling out? Do we have to?
This is the part of the lecture which I don't like. It's going to be wishy-washy. Yeah, it's like, you do whatever you want to do. This is the story that we are telling. You can sample. It's going to work. Is it easy to sample? Like, is this really practical to sample? I'm not sure about that. Yeah, I would roll out. I would need to do something like that. Maybe you can recycle samples. No, it becomes messy. Maybe you're going to be biased, and then you have to deal with the bias of the gradient, and how big is that, and it becomes very messy. But if I just tell you the high-level story, it's beautiful. So let's stop here. Yeah. So this is sort of the story. This is like storytelling. A bunch of lectures ago, when I was talking about, I don't know why it came up, but we were talking about numerical methods. Oh, curves of dimensionality. It was curves of dimensionality. Then I pointed you to this lecture by Kenneth Chad, which was about, curves of dimensionality with dynamic programming. Does it exist? Like, how do we tame it? And then he was talking about Monte Carlo propaganda. I really like that phrase because it really expresses the sentiment that this is like the propaganda, like that we're gonna remember. It kind of sells you the idea. This is not Monte Carlo. This is kind of like partly Monte Carlo propaganda because no, we have variance and whatnot, and maybe we should worry about that. And also part of like gradient descent solve problems propaganda. So we're merging two propaganda, so it becomes even stronger. It's all good. So that's how you elevate things.
More innocent question, but where does this trick in probability come from? Like, why in probability to decide they're going to take the derivative?
This is the Monte Carlo propaganda.
Okay.
Yeah, that they wanted to just sample.
Okay.
And so if you really have big space, and actually sometimes it can work, like so it's, propaganda is not necessarily bad, you're really studying an idea. Okay,
Works well for integrals.
huh?
Works well for integrals.
I mean, so that's Kenneth Schatz's lecture. If you go back to those slides, you will question whether it's like, okay, does it really work? But it does something, so it could be a way. It could be a possibility. All right, okay, so this is the policy gradient theorem. I think it's beautiful at this level of generality. It's some simple formula, of course it's nothing too deep. All right, so one aspect to this is that, okay, so first, when people first considered policy gradient, they were all about the stochastic policies, blah, blah, blah. And then I think David Silver was wondering about like, oh, is this really so specific to stochastic policies? And then they figured, no, it's like you can have the same thing for whatever policies. If you want, you can have, for example, so now we are moving away from A being a countable space. Maybe A is a vector space with some norm in it. Norm. Let's say it's a Banach space. It's like a Euclidean space. So it's a continuous thing. It's like a vector space structure. And then you could have these policies that take the form of Dirac. Right? Like, okay, I'm at state S. I just want to take this action. I really want to take this action. Like, controlling the robot, like the arm should go that way, this way. So I'm going to have a Dirac that puts a point mass at fx of S. All right, over the action space. It's like, here is my action space. It's continuous. This is my Dirac. You can't throw that. This is fx at S.
This Dirac takes input the whole action space, or infinitesimal.
The Dirac is this distribution over the action space, yes?
Yeah. I just,
So
this DA, I guess I'm just trying to, it takes
the
input.
DEA is the convenient abbreviation for any measurable subset of A.
Okay, I don't know. Okay.
So instead of writing that, it's like in the integral you would anyways write the DEA. So it's like, why not use the DEA for these two purposes?
So you're like integrating your
and
sum
at the
over.
level of French school, yeah.
Okay, and then you just, over this whole space, you assign a point mass wherever f of x, whatever value fx of x.
Right, so the way to think about this is that like whatever subset, measurable subset of A you would want to have here, you can have that there. And here this Dirac is going to evaluate to 1 if this point is in that subset, and otherwise it evaluates to 0, that's it. It's like, are we hitting this subset or not? So, and that's the needle, right? Like you will have the needle there, that's a Dirac. And then you just read out what the theorem says. Okay, so now we need to take the derivative here of this thing. So this is the policy, apply the Q function. If the policy takes the form of a Dirac, you're integrating with respect to the action, what's happening? What's the result of this integral? So you have this Q function, so m of, sorry, okay. So let me be more specific. So what's the value of this when pi of x is just this Dirac? It's like you imagine an integral with respect to this pi, and the pi happens to be the Dirac that puts a point mass at fx of s.
It's just equal that.
Q of
Whatever it
P,
is,
theta dot at
S,
s, comma, fx of s. That's right. And now the hard work that is left to prove the deterministic quasi-gradient theorem is to take the derivative of this. And so, if Q is differentiable with respect to the action component, take the chain rule. So the derivative of this is going to be the derivative of the Q function with respect to the action component evaluated at, of course, fx of s times the derivative of f. Assuming both are differential. So we can apply the chain rule. Right?
Is it ddx in front of the q pi? It says d partial a.
Well, total or partial derivative, it doesn't really matter.
Okay.
In this case, it's just, this is the only parameter.
And the one for the,
Here?
no, the one next to it. The next partial.
Here?
Yeah.
Here it's partial because there is S and A, so
Oh,
so
okay, so
call
that's-
that partial. That's an A.
Okay, that a is supposed to be, that's okay.
Yeah. So the like symbolically, Q is a function of S and A, and so we are taking derivative with respect to the
A component.
A component. Here, the French people didn't invent a much better notation. They should have some notation that I also knew, is that you can just like number the arguments and then you take the take the partial derivative with respect to second argument.
Okay.
So then it would be that of 2 or whatever. Because I'm like, what are these names? Like it's kind of crazy, this notation. I think that the hardest part of all of this is just remembering which school are we using when they're using these notations. Okay? It's clear? All right. Okay. So that's cool. So this theorem is really nice because it applies in all of these cases. There are some technical conditions. You should check them out. You should think about like, why do we need those technical conditions? Are there some examples when if the technical conditions are not met, then the theorem is not true? There will be some. It's kind of the same as what you would find in, like introductory calculus textbooks when they are talking about total derivatives versus partial derivatives. It's like you can come certain directions, and then like in the main axis directions, everything looks fine, and in the diagonal direction, suddenly things are not fine. So you need some conditions for these things to work. There was also another sneaky thing here, which was moving this derivative inside. This is doing integration here. And for that, you also need some conditions. Okay, I think we are done with this part. Okay. we can talk a little bit about gradient methods. We can talk a little bit about, okay, so gradient methods in general. So the PR condition. And we can talk about sanity checks. And then we can talk about a little bit about function approximation, like how to scale up. But as we are moving on, it becomes even more wishy-washy. It was not wishy-washy so far. So the study with the gradient methods is that, well, if you have nice and convex functions, okay, if convex, we're minimizing. If concave, we are maximizing. Here, J, we are trying to maximize it, so it should be a concave function, but it doesn't have to be a concave function. But if I say convex, then I just flipped everything to minimization. Okay. Normally, when we are doing optimization, we are minimizing, and here we're maximizing, so it's like, it's a nightmare to flip everything around all the time. Anyway, so maybe just for the sake of discussing optimization in general, we can switch to convex and minimization just for a little bit. And so for there, so an observation is that if, like, you want to minimize a function, it's kind of hard to minimize the function if you don't know nothing about its structure, because you could have a needle in a haystack kind of thing. We have seen that in many cases. So what is a structure which is convenient? Well, many times you can only get what people call local information about the function, which means that, well, you have the function and maybe you can point away that function at some point of interest. So that would be zero order information, or you can ask for the derivative of the function. Okay, so that would be first order information. Sometimes in first order information you also mean that you get the derivative plus the function value itself. Sometimes people just mean the derivative. It's because very often you don't actually need to know the function values themselves, but sometimes some methods actually would like to have that. So there is some variation in the literature in this respect there. And then you can have higher order methods that know more. And then there are also methods that have something, I don't know. So this is the this is the optimization view, that there are something in between. For example, you could have gradient information with noise, some sort of noise added to it. So that's like stochastic gradient methods, first order stochastic optimization problems are defined like that. And this local information, it just means that you have this point and you only learn about the behavior of the function at that point, like not globally, right? Like you're not getting information like everywhere else, just at that point. So it's local information. And the question is, okay, what is a nice function class for which, if we have local information, that kind of implies that we also have global information. And the beautiful function class with this property is the set of convex functions. Because for a set of convex functions, if you look at the derivative, and let's say it's unconstrained optimization, and the derivative, we know that at the minimum, it has to be zero. So you look at the derivative and it is zero, then you can reverse the thing. You can say, oh, okay, we found the minimum. right? So this is one reason people look at convex functions, because it plays really well with local information. And so that's kind of the story that we can also try to tell here. So we have this parameterized policy class. We want some local information, the gradient information, to help us to improve the value of the policy. And the problem is our functions are not convex or concave. Provably not so. So the second best thing for gradient methods is called gradient domination, or the PI condition. So soon after people started to look at optimization in optimization theory of these gradient methods, so how does a gradient method look like? Okay, let's say we are doing gradient Sn. Then the gradient method is going to look like this. So next iterate is the previous iterate plus some step size, which is positive, times the gradient. The gradient is just the derivative of the function, which would be a row vector. So you have to transpose it, evaluate it at, xi. So there's a gradient method. So people looked at these methods, very simple, and they were asking the question, can we get some rules for how to choose the step size so that we are making progress and then we are converging to a global maximizer in this case, let's say, because we're maximizing now. And so one of the first things is that, okay, if the step size is small enough, then we're going to make progress, but maybe we are going to choose it too large and then we overshoot optimum. Can we somehow ensure that a constant step size works? That would be really awesome. Of course, they would look at, I don't know, the quadratic case, one-dimensional. Very quickly you can discover that there are certain ways of setting the step size rule, the step size, a constant way, and one of the nice cases, just reverse engineering of like what is needed for gradient ascent or gradient descent, is if the function f is such that its derivative is Lipschitz. It's a global Lipschitz constant L. So they started to call these functions smooth. So smooth is one of the most overused words in calculus. So in the context of optimization, smooth specifically means this, but don't expect this to generalize to other parts of mathematics. Something to do with derivatives and it's like that smoothness. And the other condition was gradient domination, which is that for every, I don't know, point in the space, if we look at, so we're maximizing of how much we could gain compared to where we are, that is limited by how big the gradient is at the point where we are. So we are at this point x prime, and c is a positive constant and p is a positive constant. This is p. Yes.
Two questions. So for the soup of x, is it the soup and then parentheses of the expression, or is it the soup?
Doesn't matter.
Okay, so it's not like take the max value that x can take.
This could come out. Yeah.
Okay.
It's like you could see it as a regret compared to
Okay, yeah.
and it should be limited by the local information that we have. So if we guarantee that the gradient is small, we'll be fine. because then the suboptimality is going to be limited by how big the gradient was. So if you have these, and that was the work of Polyak, I think, mostly. This condition is also called the Polyak-Polyashevitz condition. So generalized, blah, 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 bigger stories. But under conditions like this, everything works well for gradient descent. And it's like short proofs. So that's like the general view of gradient methods and what optimization people worked out in, I don't know, 5 minutes, and then you can take classes about this, maybe for multiple semesters. So you can't give just to this, so it's like, I feel really silly talking about this. So this is all good. Can we, for example, use this in reinforcement learning, in this policy optimization context? Long story short, you can. There are some caveats, so it doesn't quite work that nicely. So some special cases. So sanity checks, special cases. So once we have this general view and approach to optimization, maybe we can try to apply the machinery. Okay, so I didn't talk about the part of in convex optimization that you could have stochastic gradient, right? So gradient plus noise, some sort of noise, and then how do you deal with that? What does it mean in terms of how you choose the step sizes? Oh yeah, so this is just like, okay, this was to ensure that some step size, and I think that step size is going to be like 1/2L or something. Maybe it's in this complex scenario, it's something more complicated, but something was related to the smoothness constant. So just that we can use a constant step size, and that's super simple. Like, the gradient methods do not stop there. Like, you could have adaptive step sizes. The very first thing that comes to mind is that, like, if you're worried about this overshooting, maybe you should do a line search. So what is line search? The idea is super simple. Here is your iterate. It is your direction that was maybe the gradient direction or something close to it. And you look at how the function varies along this dimension. It's a one-dimensional optimization problem now, and maybe you design some radius, maybe you need some global information about the function there to know how big should be the search region, but maybe, okay, you know that you shouldn't go behind this point because the function had some nice structure, but this direction you should search up to this point, and then you look at the function, how does it look like? It looks like this. You run a locus search, a one-dimensional locus search, you find this value as the maximizing value, you jump there. So that's line search. So this would call for the need to point away the function without any noise. So it's like, okay, if we can only avoid the function in noise, then it's a little bit messier. But you can do things like this, right? So you don't have to commit to a fixed step size. You can optimize the step size. And maybe, okay, we'll come back to that. Like, do we really need to know, I mean, is this direction set in stone? Like, maybe not. Maybe other directions are also good. Maybe you can search the directions. You can do a lot of things. One thing that doesn't change is it's a locus search kind of view. All right. Okay, so sanity check, special cases. So whenever we do have an idea about, okay, maybe we should do this, maybe we should do that, we can have very general derivations. One of the things we can do is that we go back to some super simple case and then check whether things work out in the super simple case. if the super simple case doesn't work out, then it's not a good sign, right? So what is a super simple case? So one is direct policy parameterization. Well, that's a really fancy way of saying that we are not doing anything. Yeah, this subject is full of these things that like complicated expressions, but so it just means that x itself, if I write it, it's going to be ugly. X itself is like just describing what the policy is. So pi x of as is x as a. So you have this SA dimensional big vector of 0, 1s, and it satisfies this condition that it's a probability kernel in the right way. And now you can apply the policy gradient theorem, and then you can ask if I could evaluate this gradient, would follow the gradient, does there exist a nice constant step size such that I converge? Because here we're not doing anything compression with the policy space, nothing really bad is expected to happen. It's just a tabular case. We're trying to solve the tabular case, but with a different toolkit, and we are stress testing the strengths of the toolkit. Like, is this toolkit reasonable? If it's not able to deal with even a tabular case, then maybe it's like, okay, it's not a good sign. So, what do we know about this? Well, after it's not simple, many papers, we know that this works. It always converges to the optimal policy. The convergence is geometrically fast, like in policy gradient. Sorry, like in policy iteration or value iteration or whatnot. So we're not losing much there, except that we are. Because the constants depend possibly really badly on the MDP itself. So there are instance-dependent constants that appear in these bonds, which are unavoidable. So altogether, this is not like policy iteration, which no matter what the MDP is gonna stop after, poly SA steps, and it's going to give you the optimal policy. No, it's like in some MDPs this takes more time. Depending on the initialization, it's going to take more time. It's not really a good idea. Doesn't seem so. All right. So maybe direct policy parameterization doesn't cut it, but maybe softmax. Oh, by the way, so if we write how the policy update looks like, so one short way of that I like to write it is that I just write the data. It's like, instead of this, just write that xi is equal to alpha I times blah, blah. Okay, so. So this is how it looks like. Think this is over the states, and this is the Q function of the policy that you have. So this is just over the states. So it's like, and then there is a projection, and add to projection back to the probability simplexes. Because for every state, you need to stay on the probability simplex. And so it says that, okay, increase the probability of the action in accordance to how good the action value of the action is, and okay, it's doing its thing, but it can be extremely slow. There is also this weighting with respect to the states, and so if this discounted occupancy measure puts a smaller weight on some state, then that thing is going to be updated in a less effective way than the others. And like, what really justifies that? Nothing really. I mean, like, why would you need to do that? I mean, almost these things are decoupling, so in policy iteration we wouldn't ever do anything like that. Yes?
So if this mu is over the states, q is over state actions of each side. Sorry, how are they?
Well, you just multiply the state component, action component is just like living on its own. So if I write it out, then it's as if this was a trivial function of the actions. So just multiply.
Okay, so it's like,
Yeah,
right.
nothing much.
Okay.
Maybe I should have just. Okay, so softmax. So if we do this with softmax, so what is softmax? So softmax is when the policy, we have seen it, it's like Boltzmann, whatever, is proportional to the exponential function. Okay. So pi a given s is proportional to the exponential function of theta sa. So normalized with respect to action component. And then the update rule is for the parametrization, and it becomes really similar. Except that I think that here you get what's called the advantage function. So the advantage function is simply the action value function minus the state value function. Again, like the state value function is viewed as a trivial function of the state action pairs. For every action it gives you the same value. It's very similar, it has very similar properties, and some people proved even a lower bound that shows that for any constant step size you choose with the softmax parametrization, there is an MDP with a big enough state space such that the number of updates before you get to any close vicinity to the optimum is going to be s to the omega 2 to the h, where h is the usual effective horizon of the problem. So this is for the discounted setting. So this is like really horrible runtime. And this is for the most benign initialization. So uniform mu, and the initial policy is like uniform over the actions. It's the most benign thing that you can ever think about. It is just that you can have this cascading like plateaus, and then you stay there, and then you stay more for the next plateau, and like these surfaces are just horrible. It's a wonder how well policy iteration and value iteration, all these dynamic programming techniques work, knowing all of this, right? Like it's such a lucky thing that Bauman didn't know about gradient methods. Maybe he would have fixed them. Who knows?
Maybe this isn't the right analysis for the problems we get.
No, these are lower bounds. I mean, so this was a lower bound. It was saying that like, okay, constant step size can only go this far.
Yeah.
So yeah, it's I guess it's pretty dire at this stage. Okay, what else do we have? Well, I mean, like there are so many studies to tell you. There is this curious case of function approximation. I don't know. We didn't talk much about the nightmare that I mean, you can't really avoid this. I mean, like at one point we were talking about the Monte Carlo propaganda, how to construct estimates of the gradient, because you don't really have these gradients in your hand, because you would need to get the action value function. If you have a simulator, maybe you can run a simulation and get estimates of all of these quantities. Maybe you can make them unbiased, but then you have to deal with the variance and this also raises a good point of whether, like, are these really gradient methods? Are we doing first order optimization or not? And my view is that not really. I mean, like, we are trying to solve, I don't know, the planning problem, simulation optimization, or whatever you call it, with whatever tools we have at our disposal. And now what we are trying to do in these lectures is that we are trying to use the toolkit that comes from optimization theory, stochastic gradient descent, to see whether this toolkit applies and whether we can get any reasonable results. But the problem itself was not first order optimization. We are just trying to map our problem into a problem which looks like as a first order. And so that the important thing is that you can do this mapping in zillions different ways, right? Like this. No one told you that this is the only way to estimate gradients. In fact, there is a whole industry of people talking about different ways of estimating the gradients. Right? Because it's not given to us. We can run a simulation to get estimates. You can do it in many different ways. Which one to choose? Well, the one that works. But even if you, okay, so this optimization results which say that even if you knew the gradient, if you're running gradient descent in a too simple way, like with constant step sizes, things are not rosy. They tell us that, okay, maybe this should be fixed first, and then we can go back and then think about how to construct gradients if we are really much into this gradient business. Yeah. Okay. So functional approximation. So that has some nice parts. But some really wishy-washy parts too. It's kind of like a very contrived story. The whole thing is a very contrived story. I think it's because we don't see the end of it. So you're kind of in the middle, and so, yeah. I can tell you like these little pieces of the puzzle, but doesn't fit in my head in a nice, complete story. Okay, so here, we're looking at a tabular case, and we had two parametrizations, two different parametrizations. If you look at what policy gradient does in the one case or in the second case, it's not doing the same thing. It's the same set of policies. Both parametrizations can represent any policies you want. But the trajectories that gradient descent is going to follow, and if you start from uniform policy, whatnot, it's going to be different. Is it nice? I don't know. Okay, so there are two spins to this. One is that, no, we don't like it. We want some unified way, just like some flow which seems to be the best. And the other is that, well, okay, maybe you can choose the parameterization to take advantage of that you can kind of massage and like get different directions and get the right directions. So there are these two different views. I like the second view a little bit better. I think that you can look at this as a potential strength, but this is not traditionally how people were looking at it. So when people face this, they were like, okay, this is really ugly. We want to remove this unnecessary variation. We should really be thinking about the most natural way of moving in a space. So what would be the most natural way of moving in a space? So that would be the one maybe that doesn't care about how you're parameterizing your policy. It's like it should be invariant to the parameterization. But is there such a unique thing? I don't think so. But so there are. So some directions are such that if you're making infinitesimal moves in the direction, then those directions are parameterization invariant. So this is like covariant directions, they're called. And so that's one possibility. If you have a space like this, then in a space like this, I don't think that there are any covariant directions. Like, it's just that you can invent whatever parameterization you want to have, and it's not going to have this invariant property. Nevertheless, there is another school which comes from old neural network theory, Amari, who was thinking about learning probability distributions specifically with, I don't know, log likelihood maximization. That's the classical example. It's like density estimation. And then you can have many parameterizations. And there he was like, okay, so the observation is that what is a derivative? A derivative is defined in a more abstract way. If you have probability distributions, they are like complex objects, right? Like, no, it's not finite dimensional anymore. Like, how do we even define a derivative over functions that the function's input is a probability distribution? It should give you a value. It's a functional. And I want to take the derivative of this with respect to the probability distribution. How do I do this? Well, there are many ways of defining gradients. But one of the standard ways of defining a gradient or derivative in mathematics, it's just like, I don't know, it's functional analysis, I guess. The name of the subject is that the derivative at point x of a function f, and x takes values in a vector space. Now, it's a norm vector space. That's the condition that we have on it. So probability distributions are fine. We can put norms on them, like whatever way we want. It's all fine. It's going to be a linear operator that maps from that space in such a way that this identity holds. Okay, so here is a norm. So x lives in this norm vector space. It's a space of probability distributions. And you can choose a norm. And if you're lucky with your function, there exists a unique linear operator. So this is denoted by this, such that this identity holds. So the meaning of this is that x prime moves to x, meaning that this distance goes to 0. The difference between the right-hand side and the left-hand side should be of little order of the distance between x and x prime. measured in the norm. Okay? It's the definition of the derivative for functions that are defined over these more complex things. So now you can choose a norm. And however you choose a norm, a derivative may pop up. If you choose the norm differently, a different derivative may pop up. Because choosing the norm is going to give you a derivative. And so if you have probability distributions, one special norm is, I don't know, you could have, I don't know, the alpha norm. Right? It could be the alpha norm is maybe that doesn't seem too natural. So standard gradients for vector spaces, they're just defined in the same way as here with respect to the 2 norm. In a finite dimensional space, every norm is equivalent with every other norm. So it doesn't matter what norm you choose. You will always get the same derivative. Right? So it starts to matter if you have infinite dimensional spaces, like spaces of probability distributions. Now, okay, so you could choose the 1 norm. Well, Amari, I think, went below that or beyond that, and then he was saying that it's more natural to measure distances in an asymmetric way with the chaos. With the chaos divergences. And so that leads to the notion of natural gradients. So people in the reinforcement learning literature learn about Amari's work. They found it beautiful. And they're like, oh, maybe we can try this. It's going to work better. So what is, how do we apply this in the context of policy gradient? I'm like, we have the same problem. Parametrizations determine how we're moving in a space. Amari is preaching that you should just use the KR-induced notion of the derivative and follow that derivative. And if you do that, then nice things are going to happen to you. Was that ever proven? I don't think so. He has a bunch of examples. The most convincing one to me is when he is running experiments with independent component analysis. It works out beautifully in that case. It's like before, like gradient descent was really struggling solving that problem. It's a specific unsupervised learning problem. It's a very interesting problem too. And with neural networks and whatnot. And after he introduces his machinery, the equations simplify, everything works much better. So there was a lot of excitement about this, much less understanding. But excitement goes a long way. This was transported to reinforcement learning. And long story short, if you transport it to reinforcement learning, then in some special cases you find something really interesting. So we have to choose some kind of metric which is similar to the KL, but it is not really KL because we have this space of policies somehow. And you choose this metric, and then you transport the ideas of Amari, and then you can arrive at an algorithm which is called natural policy gradient. So in the natural policy gradient method, you have a parametric class of policies, pi x, as before. And in every iteration, you have to solve an optimization problem. And the optimization problem takes this form. So we're getting this W. I think, so you have your current policy pi I, or pi of, I don't know, theta of I. And you make up some features which are based on your policy parametrization so this is just like some feature function which changes with the parametrization. So, sorry, this should be theta I. So we are at parameter theta I. And it happens to be the score function of the policy. So beautiful. You take the score function of the policy, you treat the score function, so that has d components because we are taking derivative with respect to d parameters. For every state action pair, you get d components. You call that a feature function. You multiply that with, I don't know, w, and you want to fit this to the action value function. We already seen the action value function making an appearance, and you fit it with least squares to the action value function weighted by the discounted state occupancy measure with respect to the last policy that you have. So beautiful. And then you just update your parameter the most natural way. Just move in the direction of W. So in the special case of the tabular case, you get back the same update that as we had before. And so this is called the natural policy gradient method. Shamkakadi proposed it. In his paper, he shows a very nice example where policy gradient would take forever to optimize some policy in some two-state city case. And if you run this natural policy gradient method, you will see that this converges in a much more efficient way. But the theory kind of stops here. I mean, like, there was no theory, really. Yes?
So is there extra computation in this step compared to just regular calculation?
I don't know what we are comparing, right? Like, none of this. So this is what the really wishy-washy thing is. Because none of this is like real algorithms. These are kind of like a bunch of ideas thrown together. You could do the gradient computation this way or that way. Which one? So you choose it.
Somehow find that argument, I guess.
Yeah, I mean, like maybe that's almost as cheap as doing everything else. Who knows? Maybe it's hard to compare these things.
So maybe I can ask it like in that example that gradient descent takes forever as the natural policy gradient works better, it doesn't take forever. The way they implemented that thing is
Right. I suspect it still takes forever. But it's not the extra computation that costs you that much. But it is this weighting that unnecessarily downweights states that your policy is not going to. So it's not doing any work there. Why not? It's like you're doing a lot of calculations with the advantage function or the Q function or whatnot. You calculate it at that point too, because you have to calculate it everywhere basically. We're doing a tabular thing anyway, so it shouldn't be a problem to calculate it. But then you multiply it with a very, very small number. Like, okay, that makes no sense. you're kind of ruining it. And that problem didn't go away. So I think that the problem is here. In fact, if we take some more leaps, then we can very quickly arrive at something that we know and have analyzed, which is polytech, right? So if this was just linear features, like you forget about this coupling, and you replace this by just the action value function, then you are at the same, and forget about this, right? Like replace this with optimal design or something clever that varies about how we are generalizing over the states. Then you arrive at the method which behaves in a reasonable way. So it's like, it's pretty close. It's not quite there. Yes?
I was just going to say, shall we move on to the questions? Or
Yeah, we should actually. Yeah, I didn't plan to take that much time with this NPG, but anyway, so if you do this replaced by 5, this replaced by Q, this is called NPG Q. And if you replace this with new hat, then we call this polytech. All right, good. So let's go with the questions.
No, I guess you can ask the first one.
Yeah, that was a bias something, but I didn't get it. So
Yeah, so that might be getting the wishy-washy, but I was asking if there are other, like, so in the lecture notes we have like these things that like these other methods introduce some bias to the gradient, like these different optimizations but it's still correlated with the, like it has a positive dot product with the gradient, and because of that we get good guarantees. And so I wanted to ask if there are like other sources of bias maybe from that business of estimating the gradient, that for which we can still ensure, that the result still has a positive dot product with the unbiased gradient.
maybe.
Maybe.
I don't know.
All right.
Yeah.
I think it.
That wasn't too easy. Answer.
I think it's kind of explained here, but in the argument of MPG, like we are transforming the different parameterization to the direct policy parameterization and compare the gradient directions, right?
Not sure I'm following which.
Like in the argument of MPG, like
Okay.
before you introduce the Fisher information matrix.
All right.
So like there is an argument that we transform different parameterization to a single space compared to the gradient
Okay.
directions.
Okay.
I'm not sure why we are doing that.
Oh, that was just this pondering about like what's the meaning of all these parametrizations. So a unified way of viewing at all of this is that you can momentarily forget about the parametrization. So now you have all the policies. You make a move there, and then maybe you get back to the restricted space. And if you're making a move in the unrestricted space, how would that look like? And if you do this projection back, but so what's the purpose? The purpose is just that observing that, well, there are all of these different things, and it's not very clear whether one is better than the other. And apparently, I think that there could be something that, like, if you're clever in choosing your parametrization, you can fix all of these problems. But we just haven't encountered it because the parametrizations that came to us naturally as first attempt do not have good properties. I think that the only important thing is that the choice of the parameterization does matter. And the other thing that I would say is that there is the propaganda that there is a best way of doing things. I don't buy that. Like this, I don't think that. I don't see the evidence. There is one theoretical result that somehow say connects mirror descents with natural gradient methods, but that seems to be weak too. We can talk about it more offline. Yeah.
Next one, Young
Yeah, so my question is that in some policy gradient method, we also learn the value function. For example, after critic method, we also estimate the value function using PD update. And these value functions also move towards the optimal value function when the policy is increasing optimal policy. So I'm wondering that whether this kind of value function will help us improve the theoretical guarantee of policy gradient method, or like can we use this kind of?
That is a good question. I don't know whether they are helping us necessarily. So the difficulty is that we already chose a parameterization for the policies. So you're given one parameterization. That was supposed to help us to generalize to unseen states. So we want to compete with the best policy in the class. And the reason we chose a parameterization because we believe that somehow there exists some parameter such that with that parameter there exists a good policy and it would be just enough to compete with that policy. So we are kind of already addressing the part where we need to generalize across different states. And normally when we do this value function approximation, we try to do the same, right? Like we want to kind of extrapolate to unseen states. So no, you can introduce this, but maybe they're just going to hinder things, not necessarily helping. There could be finite time effects, like, okay, maybe the variance of estimating, if you're thinking about how we can estimate the gradient, we need to estimate actual value function. We can do a rollout. It's going to have some variance that's related to the effective horizon. That's a factor of age in the bound, probably, if you do that. If you're worried about removing a factor of age, then maybe introducing function approximation and doing it in a rank way can help you eliminate a factor of age, but the effect is not necessarily bigger than that. It could also be that you introduce the right sort of generalization and then you go faster than without it, but it's like betting on being lucky, which is fine, but yeah. So there are these effects. It's a good thing. I don't think it's very much. I mean, at this very high superficial level, it's understood, but not really beyond this. But I'm not even sure whether you can say much beyond this. People do use function approximation for these two purposes: extrapolation and variance reduction. Regarding variance reduction, there is this baseline. I don't know, like, are we going to have a question about the baselines? I didn't even talk about the baselines. I don't think that, I've not seen that question. Okay, so there was this big industry of gradient estimation, baseline variance reduction. It's like, yeah, don't buy it. Yeah, if you're estimating the value function already, it's like, it's hard to see how you can reduce the variance much more in an informed manner. Okay.
Last one.
Okay. I was wondering, are there any results for continuous state and action space? Because, like, the only hope, the only things we consider that will be continuous is this policy parameterization, and we can like parameterize continue actions policies. And I was wondering, would
discretization help like ensuring the method that based on valued functions to achieve some kind of optimalities in this continuous settings. If we discretize the state space and action space, if given that they are bounded. And I was also wondering, is policy gradient like has any advantage in this continuous setting?
I think that, okay, so let me start with the second one, because I should have said that probably at the beginning of the lecture, or at this point. So a lot of people are pointing to the DP methods, the deficiency of the DP methods. Theory seems to be that they want to, that they tend to work or designed for finite action spaces. So a lot of times the methods are somehow becoming too peculiar, and then they are really exploiting that you have finitely many actions. We have seen lower bounds that suggest that even moderately many finitely many actions could be too much. So maybe there is a good reason why you should keep the number of actions finite without introducing further structure. But at the same time, people also say that, okay, like one easy way of overcoming this is to just look at policy gradient methods, because now just this part that's written here and then was kept on the board shows that you can apply policy gradients in the continuous action setting. No problems. It's really easy. It's very natural. I guess if you want to show that these methods actually do something and they work, you would need some further structure for how the action value function behaves with respect to the action component. Because you can easily have a needle in a haystack problem just searching for the optimal action there. And then, of course, the whole problem is much more complicated than that. So some further structure is needed. This is very much under researched, except for LQR and some small variations of LQR, which are beautiful, but like their significance is like beyond showing us that there could be something there with the continuous case. It's a little bit unclear. But I think that it's a very, very nice and interesting direction to try to find other problems that have additional structure that could help us deal with continuous action spaces. I just wish I knew how to do that better. Continuous state spaces or big state spaces never bother us. We are only writing things for a finite case for convenience, not for any other reason. So policy gradient plays well. I mean, the regularity conditions, you need some additional integrability conditions for the terms to go through, but that's it. So it's so there like somehow there is a big asymmetry. I mean, like, okay, having a large number of states can induce needle in a haystack in certain ways, but it does it in a different way than having a large number of actions. I think having a large number of actions is even more cruel than having a large number of states in a way. If you can say that.
I think if you have continuous actions, like then you would have continuous states, because like.
No, I mean, like you can discrete. I mean, like you can round the results and like you can have anything between.
Okay.
Yeah.
Like transition to the same state, that kind of stuff.
Yeah.
Okay.
Yeah.
Okay.
It's like rounding. It's like it's just like ugly functions. Then you will have ugly functions. I guess maybe that's what you're thinking, that if you want something beautiful with continuous action spaces, you probably want continuous state spaces, or you will get something ugly.
I mean the continuous one. Yeah.
Yeah. You could have, you know, dynamics, like, so the state space dynamics that people write, right? So here is noise, here is state, here is action. This function f could be anything.
Wait, why do you take noise? Why is the noise not part of the model?
This is the most general.
Oh, okay.
You could also, I don't know, make it additive.
Yes,
I don't know. Doesn't matter. So here you can make a continuous and S could be discrete. Yes, it does happen in some applications. Like, for example, I don't know, queuing problems. You should look up the talk of Sean Mine. It was like 3 weeks ago at the Area Theory seminar, which every one of you must be following. Anyways, it's the most awesome seminar ever, every Tuesday. And he was talking about, was trying to apply this machinery exactly that I was talking about to simple queuing problems. It's like you want to, I don't know, minimize the waiting time for customers joining some server, and then you're optimizing some parameter of the server, which is continuous valued. It's like how, I don't know, frequently the server is serving customers. It's continuous valued. And nothing worked.
Oh, okay. So
Nothing worked. That's what he says. So it's when I see something like this, made a claim, and I light up. I'm like, wow, okay, that's great. Something to look at. It's the simpler the problem, the better it is. Okay, maybe it's going to be a silly fix, but the chances are good that maybe you can find something interesting. So you should really look it up. It's pretty interesting. Right, that was the last question?
Yeah.
Okay, good. You're sort of